video something that's by reaction mechanism, reaction rate, reaction rate law, and rate determining step. So what we're looking at in this half of the chapter is, again, we go back to our collision theory. Okay, so remember this stuff. In order for reactions to occur, the particles have to collide and you have to have effective interactions. Okay, how often you can get these interactions determines the reaction rate. So that's what the second half of the chapter is going to be dealing with. Okay, and remember, energy is needed to break bonds, and energy is given off or released when bonds are formed. Okay. So, a reaction mechanism. This is basically a series of reactions that show you step by step how the overall chemical reaction occurs. Okay, so basically, is it just one step or is it a series of steps? Okay, so for example, this reaction right here, iodine plus hydrogen gives you hydrogen iodide gas. Okay, now it's proposed that it could occur by one of two mechanisms. Okay, the first mechanism says that iodine breaks up into iodine atoms, then two iodine atoms reacts with hydrogen and gives you hydrogen iodide. Okay, and if you note, just like what we did with the Hess's law problems, you can cross out things that occur on the left side and the right side. Okay, and then if you add them up, you end up with that as your net reaction. Okay, or mechanism 2. Okay, first step still the same. Iodine breaks up into iodine atoms. Then one iodine reacts with hydrogen and gives you this compound right here, H2I. Okay, then the H2I reacts with another iodine and gives you hydrogen iodide gas. Okay, and again, we can cancel out iodine and iodine with two iodines there. Okay, and the H2I cancels out with the H2I, and we end up with the same net equation on the top. Okay, now how do you know which one is the correct one? Has to be verified through experiments. Okay, now these things are called intermediates, the things that we crossed out, the iodine atom and this H2I molecule. Okay, these are not these are stable substances. Okay, so but they do not appear in the overall reaction. Okay, now each one of those steps that we looked at, those are known as elementary reactions. Okay, they must form an activated complex. The activated complex is not an intermediate. That's different. Remember, this is not stable. This is stable. These things can actually exist. Okay, but you don't see them because they're the product of one reaction, one of these elementary reactions, and then they turn into reactants for another elementary reaction. Okay, and remember, the activated complexes are not stable. These are transitional structures. Okay, so rate determining step. We're looking at how fast the reaction goes. Okay, if you have a multi-step reaction mechanism, meaning the reaction takes place in more than one reaction, the reaction can't go any faster than the slowest step or the slowest elementary reaction. Okay, so that will be the rate determining step. Okay, the slowest one is the rate determining step. Okay, so here's an energy diagram for a reaction that has more than one elementary reaction. Okay, so how many are there? How many steps did this take? Well, there's 1, 2, 3 activated complexes formed. So that means this is a 3-step reaction. Okay, 3 elementary reactions, or a 3-step mechanism. Now, how do you find delta H for the reaction? Simple. It's still the difference between the energy of the products and the energy of the reactants. Okay, products end up with a higher, so this is a positive delta H. Okay, now reaction rates. Okay, now reaction rates fall under a area called kinetics, chemical kinetics. Kinetics will study the reaction rates and reaction mechanisms. So a rate is how fast does something change, and what are we looking at? So to determine how fast a reaction goes, we look at the change in concentration of reactants. how fast do those concentrations change per unit of time. Okay. Since the nature of the reactant collisions determines how often reactions occur, changing the frequency and the energy of these collisions will change reaction rate. So if you can make the reactions collide more often, or you can change the amount of energy involved in the collisions, you can affect how fast the reaction goes. Okay, so 5 factors can influence the reaction rates. Okay, 1, you can't change, just the nature of the reactants. Some of them, if they have real strong bonds, they're not going to be able to react very quickly because you need a lot of energy to break those bonds. If other things are less stable, then they'll have less energy, so the reactions will probably go a lot faster. Okay, now, if one of your reactants is a solid, since only the surface can react, if you can increase the surface area, basically crush it, you can increase the reaction rate. Concentration. Okay? If you increase the amount of reactants that you have, you can get more collisions. Okay? Fourth thing, temperature. This can have a double effect because if you increase the temperature, you raise the kinetic energy, which means they move faster and they have more collisions, or they have more collisions and they have more energy when they collide. So this is kind of like a double whammy. Okay? Both of these things are good to increase reaction rates. Okay? And the fifth thing you can do, use a catalyst. What's a catalyst do? Okay? Remember, a catalyst does not participate in the react, or does not get changed in the reaction. It can participate in the reaction. How does it make the reaction go faster? Simple. It lowers the activation energy. In other words, it gives the reaction a shortcut. Okay, so just like if you're trying to go over a hill, instead of having to go all the way up over the hill, the reaction can take a shortcut. Okay, so the collisions do not need to have as much energy to form the activated complex, which means a larger percentage will be able to form activated complexes, and you'll get a faster reaction. Okay, rate laws. So for general reaction, one reactant turns into a couple products. Okay, by definition, the rate is determined by the change in concentration of the reactant per unit of time. So it's the negative change in concentration. This means concentration of A over time. Okay, or we can also do it in terms of products. How fast will the change in concentration of C change per unit of time, or D? Okay, but for this chapter, we're only going to concentrate on reactants. Okay, now, the concentration is also proportional, or the rate is also proportional to the concentration of the reactant. Okay, so we can also write it this way. Okay, so we can say rate is equal to K, some kind of constant, times the concentration of A to the X power. Okay, K is called the rate constant. This is determined experimentally. Okay, you have to run the reaction at various concentrations, see how it affects the rate, and then determine the value of K. Okay, X, the exponent, is known as the order of reaction with respect to A. What basically does it mean? If we have more than one reactant in the reaction, the rate law will always be K times the concentration of A to the X times B to the Y. Okay, now, what are X and Y? These are the orders. What does the order mean? Basically, it just tells you what effect does changing the concentration of one of these things have on the reaction rate. If I doubled the concentration of A, what effect would it have on the rate? Is X going to be equal to 0? That means concentration of A to the 0 would just be equal to 1. That means A had no effect on the concentration. If X was equal to 1, that means whatever I did to A, if I doubled it, the rate would also double. Okay. Now, if X rather, the order was second order, that means if I doubled A, whatever I did to A would have a squared effect. that means the rate would increase 4 times. Okay? Whatever you did to the A, whatever you did to the concentration, it'll have a squared effect on the rate. Okay? Now, remember this so that you don't have to freak out. How do I go figure these things out? X and Y, your exponents, are almost always going to be 0, 1, or 2. Okay? Now, how do you go and figure these things out? They have to be determined experimentally. Okay? Now, if the reaction was a single-step mechanism, or you were told that the reactions that you saw were elementary reactions, then A, or X, would be equal to the coefficient A, going back to our reaction. Okay? You cannot automatically assume that these two are going to be the same, and that these two, the coefficient and the exponent, are going to be the same. Okay? Unless you know that for sure that the mechanisms are single-step or elementary reactions. So here's your review question.